Okay, Chapter 7 is on systems of linear equations, and Section 7.1 is on developing systems of linear equations. So first we need to know what a linear system is, and a linear system is just basically a collection of two or more linear equations. So if you have to identify in the first question here which of the following systems are linear systems, you need to be able to determine if the equations that are in those systems are linear equations or not. If they're both linear equations, it's a linear system. If they're not both linear equations, or if one of them is not a linear equation, then it's not a linear system. And just to remind you that the forms of a linear equation that we learned in Chapter 6 were your slope-intercept form, y equals mx plus b. That's the form of a linear equation. And then you have the slope point form, which is y minus y coordinate of a point equals slope outside of x minus x coordinate of a point. And then you have your general form, which is ax plus by plus c equals 0, where the a has to be a whole number and b and c can be integers. And the other form that we just briefly introduced but didn't do a whole lot with was standard form, which is similar to general form, except the constant is on the side of the equation by itself. So those are all forms of a linear equation. So if we look at the first example A, x plus y equals 14, that's the standard form of a linear equation, so that's a linear equation. And 2x minus y equals 10 is also standard form, so that's a linear system. B has a linear equation, the first one. It's not written in general or standard form, but it's kind of in between both of those. But if you move that one over and write it as 2x plus y minus 4 equals 0, you would get a general form of a linear equation. So that is a linear equation, and the second equation is in standard form, so that would be a linear system. Both the equations are linear equations. This one here, in C, there are squareds with your variables. So this is not linear. So that means that this is not a linear system, because one of the equations is not a linear equation. So if one or both of the equations are not linear, it cannot be a linear system. And the last example there, it's not quite again in either one of the forms that are listed above or that we learned in Chapter 6, but you can easily put this into general form if you multiply through by 4 and get x plus 4y minus 12, multiply everything by 4, equals 4, and then bring that 1 over. You could see that this could be written easily in general form, so that is a linear equation. And this one is in slope-intercept form, so that is a linear equation. So the only one that isn't a linear system is example C. All right, so the next thing we're going to do is learn about how we can write equations, linear equations, because a lot of times when we're using linear systems, we're solving problems. So this first section is going to kind of teach us or give us some practice on writing equations to represent information. So the first example says the information that you're given is that John bought 8 books. The softcover books cost $13, while the hardcover books cost $24, and he spent a total of $209. It says we can write a system of linear equations that could represent the given situation, and then we can use the linear system to determine the number of each type of books that John bought. So basically, when you're given that information there, you know that he bought 8 books in total, you know the cost of each type of book, and you know the total cost, but you don't know how many of each type he bought. So those would be the two things that you're looking for. So the first thing we're going to do is assign variables to the two things that we're looking for. And I'm going to assign B to the number of softcover books and I'm going to assign H to the number of hardcover books. lot of times you use letters that would kind of help you remember what the variables stand for. But I didn't want to use S for soft cover because some people think your S is a 5 when you're copying someone else's work or whatever, when people are copying it down from the board. All right, so the next step asks you to use the given information to write 2 equations relating the unknowns. So if we were to go back and take that information and see if we could come up with 2 equations that would kind of relate the variables that we're talking about here, we do know that John bought 8 books. So that would mean that one equation would be B, the number of softcover books, plus H, the number of hardcover books, should be 8. And the next thing we have is information about the cost of each and the total cost. So when we buy things, we know that we need to know the number of items and the individual cost of each item. And if we multiply the number by the cost of each, then we can get the total. So that would help us in most of these cost problems. You kind of look at for something like that a lot of times is your second equation. So in this case here, we have $13 for every softcover book plus $24 for every hardcover book, and that will give you a total of $209. So those would be the 2 linear equations to make up our linear system that we could actually solve to figure out how many hardcover books and how many softcover books John bought. But we're not actually going to do that right now. That's what we're going to learn in this chapter, is how to solve a system, a linear system. So this section, though, is just practice on writing the equations that go with the information. All right, so some examples related to that you can try are, first is, once you're given a system, knowing whether or not a point is a solution to this system. In order for a point to be a solution to the system, it has to satisfy both equations. So we're going to take the first equation there, and we're going to plug in this x and this y to see if this is a solution to this system. So if we check the first equation, I'm going to call this equation 1, and I'll call this equation 2. So if we check in equation 1, and we sub in 8 for the y, and for the x we put in 1, so plus 5. If we look back at equation 1, it's y equals 3x plus 5, so that would become 8 equals 3 times 1 plus 5. And if we check that, 8 equals 3 plus 5, 8 equals 8, and that's a true statement. Okay, a lot of times I'll just put a little question mark there to show you that you're checking to see if they're equal. We don't have a whole lot of space here. Some people work like we did in the last chapter with break it down with a line, left-hand side, right-hand side, but we don't have a whole lot of space here, so we'll just do it like that for today. And the second equation, we want to check x equal 1 into that equation, so it'll be 6 times x would be 6 times 1, minus 5, we go back, it's 5 times y, so that would be, in this case, 5 times 8, and we're checking to see, there's a question mark there, checking to see if we get negative 43. So if we check this side, we get 6 minus 40, and we know that that's not equal to negative 43. So therefore, this is not a solution to this linear system. Okay? So therefore, not a solution. The next equation, next point, that we're going to try is negative 5 for the x and 3 for the y. So if we plug that into the equation, the first equation, we get 3 equals 3 times a negative 5 plus 5. So we're checking to see if that's true. Question mark 3. On this side, it's negative 15 plus 5, and negative 15 plus 5 is not equal to 3. 3 is not equal to 10, negative 10. So therefore, you don't even need to bother to check in the second equation, because if it's not a solution in the first, it's not going to be a solution to the system. So therefore, not a solution. To the system. And the next equation, next point, is 2, 11. So the x is 2, the y is 11. So if we check it in the first equation, 11 equals 3 times 2 plus 5. 11 equals 6 plus 5, and that is true. Should have a little question mark there. So that is a true statement. So then we check in the second equation. That's equation 1. And then we check in the second equation. We have 6 times 2 minus 5 times y was 11. And we're checking, question mark, is that equal to negative 43? So this would be 12 minus 55, which is equal to negative 43. So that means it works in both equations. So therefore, 211 is a solution to the linear system. Okay, so the next question is going back to coming up with the right equations to match your information. So the first example there, number 2, asks, gives you the information. Sorry, Dominique bought 7 tickets to a puppet show and spent a total of $43. If children's tickets cost $4 each, while adult tickets cost $9 each. So we're just going to underline that so we know. Which linear system could be used to model the situation? Now there's a mistake here in this. It shouldn't be, we know the cost, we don't know the number. So this should be number of adult tickets bought. And C should be number of children's tickets. Okay, not the cost. We already know the cost. The cost for children's was $4, and the cost for adult tickets was $9 each. So if we have to come up with equations to relate this information, we know that Dominique bought 7 tickets. So that would be, one equation should be A plus C equals 7. So we've got a couple of systems here that have that equation in them. Then we need another equation that relates the cost and then mount the number of tickets bought and the cost to the total cost. So we would have $4 for every child ticket, so 4C, and $9 for every adult ticket, so 9A. And if you add 4C and 9A together, you should get $43. So if you look closely at the two that we've identified have one equation, A plus C equals 7, the correct one would be the one in B, because the 9 is with the A and the 4 is with the C for 4 for children's ticket. This one here in C, question C, the system C is wrong because it said the adult tickets were $4 each and the children's tickets were $9 each. We want B. B is the one that relates to information correctly. Okay, question number 3. The test has 20 questions worth 100 points. The test consists of a number of true-false questions, and that's going to be represented with T, the letter T, to represent the number of true-false questions that are worth 3 points each, and a number of multiple-choice questions. M is going to be the variable that we're going to use to represent the number of multiple-choice questions, and they're worth 11 points each. Which linear system could be used to model the situation? So we basically have the number of questions. There's 20 questions in total. So we should be looking for the variable T, which is the number of true-false questions, plus the variable M, which is the number of multiple-choice questions. That should add up to 20. So T plus M equals 20 should be one of the equations. And if we look at all the examples that they have given to us, none of them have that exact equation there. So you have to look at each example and see, well, is there one that I could rearrange so that I would get T plus M has to equal 20. So if we look closely at each of the examples, the one that can be rearranged correctly would be the one in D, because I could easily bring that M over and get T plus M is 20. Okay, if I bring the T and M on the one side for C or A, I'm not going to get T plus M equals 20. All right, so it looks like D is our answer because that's the only one that has that information corrected, displayed correctly. But we'll just check to make sure that the first equation is right. So it tells you that the true-false questions are worth 3 points each, and the multiple choice questions are worth 11 points each. So that means that 3 times T plus 11 times M should add up to the total of 100 points. So equation 3 times T plus 11 times M should add up to 100, and that is the other equation that's in that example for D. So D would be our correct system. Okay, our last example on this page says Joshua invested $9,000 into separate savings accounts. One account earned 5% while the other earned 8% per year. Last year, the two investments earned a combined total of $800 in interest. Which system of equations could be used to model the situation? So we're going to let X be the amount of the 5% investment and Y be the amount of the 8% investment. So the first equation should be that the amount of 5% investment plus the amount you invested at 8% should add up to $9,000 because that's the total that was invested. So we're looking for an equation, X plus Y equals 9,000. So that would be D or A here. The other two don't have that equation, or anything that could be rearranged to get that. So we're down to answer should be either A or D. So now we check the rest of the information, and it says one account earned 5%, while the other earned 8%. And we know from our variables assignments that the 5% amount was X and the 8% amount was Y. So that would mean that we're looking for something that shows that 5% of X plus 8% of Y should add up to interest amounting to $800. Okay, because when we have a percent of something, we multiply that percent times the amount to get the amount of interest that was earned. So 5% of X plus 8% of Y should add up to $800. And if we look at our systems in A and D, the one that best represents 5% would be the decimal 0.05 would be 5%, and 0.08 would be 8%. So our system that matches that information would be A. Okay, in this one here, in D, 5 here would not be 5%. Okay. Example number 5 is an example about the perimeter of a barn. So perimeter, you should know from earlier years that the perimeter is the distance around. And when they're talking about the perimeter of the barn, they mean the distance around the outside of the barn at the base of the barn. So basically distance all the way around the back and sides and everything. So the distance all around the base of the barn is 72 feet, and its length is 4 feet longer than its width. So we have to come up with variables because we're talking about the length and the width here. So we're going to let L be the length and W be the width. So sometimes it helps to draw a diagram. The diagram is provided here, but if this diagram wasn't provided, I'd probably just draw a rectangle to show the base of the barn. So it says, we're going to say L is the length of the barn, and we're going to say W is the width of the barn. So now we have to come up with two equations. If we have two unknowns, we need two equations to be able to determine what those two variables are. So we have two unknowns are. And again, we're only setting up the systems now. We will learn how to solve these systems as we move through the chapter. So one equation would be about perimeter of the barn. We know that we can relate the length and the width using the statement that the perimeter of the barn is 72 feet. And you should know from your earlier work with perimeter in junior high that perimeter of a rectangle is 2 lengths plus the 2 widths should add up to 72. That would be one equation. And then the other piece of information comes from this statement right here that says the length is 4 feet longer than the width. So the length means equals 4 feet longer than the width. So that would mean to take your width and add 4 to it. So those would be your two equations that could model this information. And when you have two unknowns, you need two equations to be able to determine those two unknowns. So question B says Dylan has determined that the barn is 20 feet long and 16 feet wide. Use the system that you created in A to verify that Dylan is correct. So we would take our equations. I'm going to call this equation 1 and this equation 2. So in equation 1, we're just going to let the L be 20 and we're going to let the W be 16. So in equation 1, if we put those values in for L and W, we get 2 times 20 plus 2 times 16. And we're going to question, is that equal to 72? So this gives us 40 plus 32, which is equal to 72. That is correct. Then we check it in the second equation. Is the length equal to the width plus 4? So we check, is 20 equal to 16 plus 4? And it is. So that means that the dimensions that Dylan gave were correct. Question number 6 says the residents of Porkchop held a weekend fundraiser and raised $72 by collecting 2,000 items for recycling. They received 3 cents for each aluminum can and 5 cents for each glass bottle collected. Create a linear system which could help to determine the number of cans and bottles collected. Remember to state what your variables represent. So again, we have 2 things we don't know. We know how much they got for each aluminum can. We know how much they got for each glass bottle, but we don't know how many of each of those things they got. So that would be what our variables would represent. And I'm going to use C for the number of aluminum cans. And I'm going to use B for the number of glass bottles. I mean, it doesn't matter what variables you use. You could use X and Y if you wanted to, or you could use A for aluminum and G for glass, but I usually try to let it equal variables that I'll remember that C stands for can, B stands for bottle, you know. Okay, so if you look at the information they've given you, you know that they collected 2,000 items. So one equation would be that C plus B is 2,000. Because the number of cans plus the number of bottles totals 2,000 items. And then you know how much money they made. And again, when you're talking about total money, it would be the number of items times the cost, or in this case, the value of each. So this one here we have, for each can we got 3 cents. But now, you got to be careful here because this is in cents, but this is in dollars. So we have to make sure they're both in the same units. So that would mean that we would write, instead of 3, we would write decimal 03. For 3 cents in dollar format would be decimal 03. So that would be for every can, and then for every bottle, it would be decimal 05, and that should equal a total of $72. So those would be our equations. Question B says the residents believe they collected 1,400 cans and 600 bottles, but are not completely certain. Use the linear system to determine if those values were correct. So if we go back into our system, if we call this equation 1 and this equation 2, we have that C equals 1,400, and B, they're saying, was 600. So if you check in equation 1 is C plus B, and that does equal 2,000. That is correct. Then if we tried in equation 2, we have decimal 03 times C was 1,400, and decimal 05 times 600, and we're checking, is that equal to question mark 72? So if we look at what decimal 03 times 1,400, that gives you 42, and decimal 05 times 600 is 30. So that does equal 72. So therefore, they were correct that they did collect 1,400 cans and 600 bottles, because it matches the information that we had for our systems. Okay, so the last example here now is kind of one that shows you how you have to be careful how you write your equation sometimes and make sure it matches the information. So for his new home construction, Frank needed to build a ledger board to attach his wraparound deck to his house. He needed a total of 280 feet of lumber, but the store only sold them in lengths of 8 feet and 12 feet. Frank noticed that he had twice as many 8s as he had 12s. So to represent this situation, Frank developed a linear system. He said 12 T plus 8 E equals 280, and 2E equals T. And E represented for him the number of pieces of 8 foot lengths, and T represents the number of pieces of 12 foot lengths. So Frank's wife Enid tried solving the system and got the solutions E equals 8.75 and T equals 17.5. And when she checked the solution with Frank's equations, the values did work to solve the system, yet Enid knew there must be a problem since there were supposed to be more lengths of the wood measuring 8 feet. Plus, she cannot purchase partial lengths of wood. So she knew that there was something wrong there, because he had more, he had twice as many 8s as he had 12s, but when she worked out this little system that he made up, she got E equaling 8.75 and T equals 17.5, which meant that he had more of the 12 feet lengths. So if you look at the equations a little bit more carefully to see what was the error, you do notice that 12 times the number of 12 foot lengths plus 8 times the number of 8 foot lengths should add up to 280 feet. That should be okay. But in this case, the second example, it says 2E equals 8, which means twice the number of 8 foot lengths equals the number of 12 foot lengths. And he wanted to have twice as many 8s as he had 12s. So when you think about that, that means that the 8 foot lengths should be more. So that would mean this was the incorrect equation. He should have the 8 foot lengths. Number of 8 foot lengths should be 2 times the number of 12 foot lengths. That's where he made his mistake. So just be careful when you're doing stuff like that, because if you have equations, sometimes, especially when you're doing things like twice as much and 3 times as much, like make sure you're putting it with the right variable. So in this case here, we're supposed to have more 8 foot lengths than we do 12 foot lengths. So you should have the 8 should be twice as much as the 12 foot lengths, not the other way around. Okay, so it's just to set an example that kind of shows to make sure you check your answers into your equations to make sure they make sense in terms of what you're expecting to get, and if they don't, maybe you might have a little negative mistake, or like the last example, you might have the twice as much with the wrong variable. So this is it for section 7.1, and these are some questions you can try in your text on page 401 to 402 that you can try to see if you understand these concepts.